All right. So 4 is a weight problem because we are given the material, correct? What is it? Steel? And did you look that up? What is it? How much? 490 pounds per foot cubed? Yeah, so that's almost always the situation. They're going to give it to you in PCF, pounds per cubic foot. And a lot of times your units are going to be in inches, which I think these are in inches, correct? Yeah. So just be aware of that. You're going to have to do some kind of conversion. The equation, there's 2 of them. One of them, so I would probably, put your axis in the lower left. You'll get to where you probably don't need to draw it, but I'm going to continue to draw it for a while. So here's my axis, X and Y. So that's got to go on because we're going to base everything off of that. But if we look at this horizontal axis or the X neutral axis, there is symmetry about that axis. So we could calculate a Y bar, but it's definitely going to just be that axis of symmetry, right? So if you can see the axis of symmetry, you're going to save yourself some time, especially if they're asking for Y bar and X bar. So Y bar is just going to be halfway up. In this case, since I put it down here at the bottom, it's like 2.5 inches up, right? So no need to calculate that one. If you did calculate it, you just proved it, proved symmetry. So then really what we want to know is X bar, where this thing is. That is the balance point for the system. So the reason we're doing this is we're going to need that information in the future in strength materials, because that's going to locate what we call the neutral axis. In this case, it's just locating the balance point, but the concept, the more important concept is we're going to use that cross-sectional area, and we're going to need to find this balance point or center of gravity. All right. So we need things like W1, W2, W3, and it's super helpful for me and anyone else looking at your work if you label those areas or shapes or parts to the thing. So I don't know how you did it. I'm going to just go 1, 2, and 3. So then we have to calculate these, and we also need X1, X2, and X3. And that's the location of the centers of those individual shapes, which usually you can just get kind of by observation. So you want to break it into the simple shapes that you know, like rectangles, circles, even triangles. We kind of know that we can look up that formula for the center. All right. So weight of 1, I don't know if I gave myself enough room, but if I used pi, R would be 2.5 squared. So that's the cross-sectional area. And we multiply times its length, 6 inches. And then we'd multiply times the weight of the thing. So if you put it in inches and you got this at 490, something's got to get converted, right? So maybe you put these in with feet, or you convert this to inches cubed. Doesn't matter to me at all which one you do. So I would probably go with the conversion of inches to feet, and then at least the 490. If I wrote in pins, that's not optimal. I wasn't forward thinking very well. So I know this one is going to become half foot, right? 0.5 feet. And then this one would be what? 2.5. 12 divide 0.2083 feet. Right, so that just puts it in cubic feet. Then I can multiply by the 490 pounds per foot cubed. What did you get for weight 1? if you got. That happens. Let's see what I got. 0.5 times 490 times and pi. I got 33.41. Okay. So let me just do the same for W2 and W3. So crunch out, if you don't have it, crunch out W2 just to make sure you can do it. The diameter is 3, so the radius is 1.5. 1.5 divided by 12 would be 0.125. So this one is pi 0.125 squared times its length, 8/12, 0.66, and then times the 490 for all of that. We would expect it to be less, right? It's a little longer, but it's less diameter. So I get 16.19019. All right, let's get that. Yeah. Okay, so that's just round. That's rounding. I'm good with that. All right, and then the last one, I'll just crunch. 1 inch, so it's a 1/2 inch divided by 12 to get it converted. And square that. Pi. And then length. I get 0.89. Anyone else get that? 0.891. Okay. So when you're given like what the object is, right? If you know its weight, then you would work with the weights. And that's what we're doing. The equation is for X bar, right? The summation of WX's all over large W. So that's the equation when you have mass or weight. If you don't have mass or weight, if these were just areas, and believe it or not, it would work with the areas. You could do this out of rectangles. So I'll do that just to demonstrate it. But then the same thing that you can get X bar, and we can do it from the areas because it's the same material. It's 490 each time. So essentially just kind of taking the 490 out of the equation. But it becomes areas times X's over the total area. The same formula, you're just using areas. You can get away with this when all the material is the same. Okay, but we'll keep going. So I need X1, that's halfway, so that's going to be 3 inches. What is X2? Yeah, so it's all the way over. So you have to keep your reference. Keep your axis. So it's 6 plus 4, 10 inches. And then X to the third area. Yeah, 2 and 8 is 10 plus 6 is 16 inches. So once you put that coordinate down, you have to go off it. And the coordinate can go anywhere. Like you can put the coordinate on the right side and then just go left. Kind of weird, but you could. All right, so now we have all the pieces for the weight one. So X bar is going to equal the summation of all these W's times X's. So W1, 33.41 pounds times X1, 3 inches. And these are all solid, so they're all additive. We're going to add them up. Plus 16.019 pounds times 10 inches. Okay, I'm losing that thing. And 0.891 times 16 inches. W1, X1, W2, X2, W3, X3, all over the total weight. I'm just going to add those up. $50.9391. That's 33 plus 16 plus 0.891. Now I will crunch this. Anyone confirm that number? Okay, see one head nod, two head nods. I'm going to take that. Kyle's nodding his head also, I'm sure. All right, so that's the balance point, right? You're going to put this thing into balance. So I'm going to crunch it with the area formula now, just based on these areas. And I can do that because the material is not changing. It's 490 all the way through. So this is probably the more common formula that we run, is this summation of AX's times A. So I got to move this a little bit. Hopefully I can still keep, I'll put it kind of tight. X bar again. So area 1, I'm just going to treat it as a rectangle. It's going to be diameter 5 inches, so 5/12. Again, I'm just getting it to feet, so 0.4166 feet times its X distance, which didn't change. It's still 3 inches. I add to it this area, which is the 3 inches. I think that's 2.5, yeah, 0.25 feet. So that's this rectangle times 8. We made an error. Nobody stopped me. What's our error up here? That's fine. This works. 333. Yeah, we're good. All right, 10 inches. Sorry, I guess I glitched. And then the last one, area is 1 inch. Don't really need to be doing the 12 divide thing, but it's all right. Yeah, I'm screwing up, but we're going to fix it all over the total area. Hopefully you'll see the mistake I'm making. We're going to add the areas up. So you see my problem. I have cross units. I really didn't need to put it in feet when you're doing areas because you're going to have square inches down here. So I don't want feet times inches. So I didn't need to turn it to feet. I could just leave it in inches. So this, the first one can be 5 inches. The second one can be 3 inches. And the last one can be 1 inch. So in the end, you just want square inches. So I needed to convert it to feet up above because I used the 490, but down below, I don't use the 490, right, with the areas. So sorry about that. Probably confusing as heck. So it is A times X. So I have 5 times 3, but I never did the area. Yeah, I need to start over. Sorry. That was bad. Maybe I can fix this problem. Sorry, Kyle, screwed that one up. Reset yourself if that's possible. So that's the formula. So we got to have areas times X's, and I didn't even have areas. So area of the first one is going to be 5 inches times 3 inches. Oh, sorry, 6. 5 times 6, the length. All right, that's the area. This is the 5 inches, that's the 6 inches. Then you multiply it by the X. So here's A1, X1. Then I add to it the next one. Area is 3 by 8. 3 inches, 8 inches. So that's the area. Then we have the X distance, which is the 6 plus the 4, 10 inches. So it needs to be an area times an X. I really mucked that up the first time. Then the last area is 1 by 4. So 1 times 4, that's the area. We're going to add these together. And then the X distance is the 10 plus 6, 16. All of that over the total area. So area, area, and area. So 5 times 6 is 30. 3 times 8 is 24. And 1 times 4 is 4. So that's 58. And that is inches squared. So these are all inches to the third. This is inches squared. It's going to leave me with inches. Whew. I mucked that up the first time. I get 6.79. Is that what you get? That's different than the first one. That's not area. Well, pi squared is, yeah, but it doesn't give you the area of the rectangle. So should be spot on the same. Now I feel like we made a mistake on the top part. No. When you punch in the, so you're punching in volume instead of area.
IR squared, but I didn't multiply by the 490.
No, right, but you multiplied by the 6 and the length. So you used volume.
Yeah.
And you got the same number.
And I got 5.46.
I like it.